Good morning, everybody. I'm glad to be here again, and this is my 7th speech at the GPD. And well, okay. I always reported about nickel sulphide, and I would say there was a development. I will show you a little bit what was the result of the last things that we did at Saint-Gobain concerning heat soak test, and this is the title. I say that the heat soak test is much better than presumed, and I will show you why. I don't have the time to present everything today. I would just make you curious about the publications that I did last year and to read that thoroughly. You can also have discussions with me after the speech. At any time, we can make a meeting and discuss that and even continue later. Okay, so I go into everything, and you have already heard about the basics, and I don't go into these details now. The only point that I would like to make is that the nickel sulphide is frozen in... no, it's not that. I go through this, and so, okay, I just go to the properties of nickel sulphide. You see an example there, and on the left-hand side, you see a fully developed nickel sulphide. You see the surface. The surface is rugged. That means it is not a smooth surface, and this has a big impact also on the mechanical properties of such an inclusion. It's different from any other inclusion. It's also different from a bubble. And if you look inside, you often see that it is diphasic. That means there are two phases of nickel sulphide, two different compositions, and one of these compositions is NiS, and this is normally assumed to be a nickel sulphide, but it's not true. What is true is that it is in most cases, it's a biphasic thing, and the second phase is not NiS, but it is Ni9S8. I will explain you why it is like that. Now, the properties I already told you, spherical. I don't go into the details. I don't have a lot of time, as I said. The density is higher than the density of a glass melt, and that means that it is going to the ground, and this limits the size, the possible size of nickel sulfides. I showed that in the publications. It limits the size to about 500 micrometers. They cannot be bigger, because if they were bigger, they were destroyed, or they are destroyed in the glass melt. And they are chemically and thermodynamically unstable in a glass melt. So, such a nickel sulphide inclusion has a property that is, it has a melting point because it is a substance. This melting point is about 1000 degrees C. 1000 degrees C is at the entrance of the float bath. That means that such an inclusion is crystallizing at that temperature. But as long as it is in the glass melt, it is at higher temperature, and this is the reason why it is liquid. Now it is not stable, and it is reacting with oxidants, for example with sulfate in the glass, and it's decomposing slowly, but it is decomposing. So we have a melted particle, not a particle, a melted droplet in the glass melt, and it is reacting. We have a composition of NiSX because it is not crystalline. This composition is not fixed. And this means that X can be any value. And it will start from high values, it will start from low values, and it will then go from low values to higher values, because this is the way oxidation is made. So what we have is, there is some other effects that I don't have the time to explain, but this is the most important. You have a droplet, NiSX, and X is variable. Variable means there are several things, and the development is from low values to higher values, and crystallization then takes place at 1000 degrees C. We have this composition, and according to the composition and according to the phase diagram, this substance will then crystallize. And we have two cases, two different cases. One case is that if there is more nickel than sulfur, then we will have a two-phasic inclusion. We have an NiS and we have Ni9S8. And if there is more sulfur than nickel, or if it is equal, then we have only a one-phasic inclusion that has a composition of NISX. X may be 1, then it's exactly an NIS, but it can also be more than 1. It can go up to 1.06. I showed this in my publications. I have no time to explain now why it is like that. So if we have that, then we can compute or estimate, let's say, a probability of occurrence of the different compositions. We have found all of those. You see pictures, SEM pictures from electron microscope, and I showed all the compositions. This is one that has very low amount of NIS. There is much more Ni9S8 in this inclusion, and in the middle is about 50-50. There is approximately pure NIS, and here we have two examples of overstoichiometric composition. So you see everything is possible, and the probability of occurrence is about as I have drawn over there. That means most of the inclusions are really NIS, but they have an accompanying Ni9S8 in different compositions. Okay. So if we have that, there is a second thing that has never been taken attention to in literature, as far as I know, because these inclusions are not only biphasic or monophasic, they also contain bubbles. Bubbles means there are voids, and the voids are caused by gas development, and this gas development is limiting the size. This is the reason why the curve that you see there is decreasing. So the estimate is that most of the inclusions contain NIS, and some are not containing it. They are overstoichiometric, but it's much lower in number. Well, these bubbles are showing the overpressure, and well, okay, as I said, I don't have time to go into this detail, but they are very important because they show a second decomposition mechanism in the glass melt, and this is the explosion of the inclusions. They have too high inner pressure, and then they will decompose. And this is the reason why the probability of occurrence is decreasing with the composition. Okay, so I made some small calculations based on literature values, and literature values are, in this case, the expansion coefficients of the different components in the nickel sulfide inclusion. As you have seen, it is not, there are at least, let's say, one species, but it can be two, nickel NIS and Ni9S8. But it can also be, if it is overstoichiometric, the overstoichiometric species has a little bit different properties from the pure NIS. This was also published in the 1960s. I think by Lafitte described the properties of overstoichiometric NIS. And if we have the transformation of the overstoichiometric NIS, the overstoichiometric alpha NIS, then there is also a generation of Ni3S4. This is polydiamide, and the polydiamide is a result of diffusive decomposition of the overstoichiometric NIS. So things are a bit complicated, but the diagram that I will show you here is more simple, because it is showing on the x-axis the composition. It is going from pure Ni9S8 to NIS. This is the straight line at 1, and then it is continuing to overstoichiometric. And well, I call this the left-hand side and the right-hand side. You see it inside there. So you will see that there are some differences. The ordinate, the y-axis, is representing the relation between the inclusion and its bubble, because there are differences in the expansion coefficient also between nickel sulfide and glass. The glass has a higher expansion, a lower expansion coefficient, and this makes that the nickel sulfide, after its production by the glass melt, has a lower diameter than the bubble that is surrounding it. There is a gap, and this gap must first be filled up, and this is what is represented by line T. This is the minimum that the contact has to be between the nickel sulfide and the glass itself. If the values are negative, you see this here. If the values are negative, nickel sulfide inclusion is smaller than its bubble. If the values are positive, then the nickel sulfide is bigger than its bubble, and this is the configuration where the nickel sulfide can lead to a breakage because it is making pressure to the glass. And the minimum pressure is, as I already said, is the line T there because there needs to be some pressure, and this was calculated by the university guys of Darmstadt. They showed that this is the minimum pressure about, this is an estimation for sure, and it can be different from case to case. Okay, so now if we look at the nickel sulfides, we see this. And this is after production. You see, after production at room temperature, for room temperature I estimated 80 degrees C, because on the facade it can be up to 80 degrees C. This is a worst case scenario that I show you now. I could also change it for better and lighter values, but this is a strong estimation at a very high risk, let's say. So you see, at room temperature after production, and if the alpha phase is frozen in, everything is uncritical. All of the inclusions, independently of their composition, are smaller than their bubbles. Now we heat up to heat soak temperature. Heat soak temperature is estimated to be 260 degrees C, and you see that the overstoichiometric inclusions are still uncritical. And even a part of the stoichiometric inclusions are undercritical, but there are some that become critical. And just have a look, it's just these inclusions that contain more Ni9S8. This is due to the fact that the Ni9S8 has a very high expansion coefficient. So it is expanding a lot, and this makes those inclusions critical, although they have not been transformed. Now, if we transform the things and we look at room temperature, then so no, this is it's after transformation and in the facade. So at room temperature, estimated 80 degrees C, you see that then the overstoichiometric, the stoichiometric, and a part of the understoichiometric become critical. But it's not those that contain Ni9S8, because the Ni9S8 has no phase transition. It is like, let's say, a filling agent that is inert, but it just has a high expansion coefficient. So this is what we have at room temperature after transformation. Now, if we look after transformation and at heat soak temperature, you see that all of the inclusions now become, this is line D, all of the inclusions become critical. Even those only containing Ni9S8 that has no transformation at room temperature, that is uncritical under any condition except in the heat soak test. In the heat soak test, it will lead to breakage. So we have, you can see that by the diagram, and then evaluated in the part B, you have more nickel sulfide inclusions leading to breakage in heat soak test than at room temperature. And the difference between both is about 39% at room temperature and 100% in the heat soak test. That means that the heat soak test is making much more glass break than would be possible in the heat soak at room temperature because of the difference in the expansion coefficients. Just this, and this is only one aspect. Okay, this is again some estimation, and the 39% mean that in the heat soak test, every pane that would be critical in a facade would break, and also there would be 1.5 times the same number as a kind of a safety margin. That means the heat soak test at 290 degrees, even only at 260 degrees, makes much more glass break than would be possible at room temperature. So this is one point. You see by that the heat soak test is something that is very safe. And if you reverse the argument, if you look at the heat soak test and you see that in the heat soak test there might be some remaining breakage possibilities, yes, then you cannot extrapolate that to room temperature, because the conditions at room temperature are quite different from the conditions in a heat soak test. If you just extrapolate that, you make a mistake. You have to take that into account. It's very important, because otherwise your safety estimation will be wrong. Okay, so what exactly happens in the heat soak test is another question. I had a chance that was a nightmare in production, I could say. This was the construction of the Peter Merian house in Basel. And in Basel, you see the picture is already there. Yes, you see that this is a very big house. It was about several thousand square meters. And well, we produced a toughened glass for that. And it was based on some kind of, how is that called? Casted glass, patterned glass for the claddings. For the windows, for sure, it was float glass and it should look the same. So we colored the whole content of such a patterned glass furnace and we made that production. And during that production, during toughening, we had a breakage rate of about 30%. Then, because it was on the facade, we had to heat soak test it. And in the heat soak test, there was another 30% of breakage. We imagined a nightmare for the producers. But for us, it was a kind of a luck because we could see that we were asked first to find out the reason for this breakage. And we found out that it was not nickel sulphide, but it was mostly inclusions based on the batch, on unmolten batch silicon dioxide inclusions. I don't have time to go into details of that. One thing is very important in this, that this is not nickel sulphide, but there are breakages in the heat soak test. And this was 20 years ago, and we had not one single breakage in this very big facade, although we had this big number of breakages in the heat soak test. So you see by that, even if you have a lot of breakages in the heat soak test, the product after the heat soak test will be safe. And there is not falsely only nickel sulphide the reason. It can also be different things. So the question is then, what is really happening there? Oh, okay, this is another diagram you see on the left-hand side. You see this is the cathedral glass, and on the other side is the nickel sulphide inclusions from standard heat soak test where we did not face this lot of breakages, and you see the curves are exactly the same. So they do not depend on the kind of inclusion that is in the glass. They just depend on that there is something that makes the glass break. Yes, so what would we expect if we would have the nickel sulphide as the basic reason of the inclusion of the breakages in the heat soak test? That is, we would have an Arrhenius curve because there is a transformation, there is a gap around the inclusion, and we would expect something like this curve. So this curve was really measured in, you see there is a one dot, sorry, oh, not going back? Doesn't matter. Okay, so this is the curve that we would expect. And this is the curve that I measured one time. This one time was in a building that was under AC. At a temperature of about 22 degrees all the time, this is the curve that we get. But this is not a variable function. This is an exponential function. So it's quite different from what we really see in the heat soak test. And if we make the calculation of the parameters, the kinetic parameters derived from this curve, we find this. So you again see the variable curves, and on the right-hand side here you see the variable curve again, and you see the curves that we would expect from the kinetics of transformation of the nickel sulfides. You see that there is a huge difference in the form, and we can also say all of the breakages, if this would be the only reason, all of the breakages would take place during the heating up. This is also the reason for my question. Did you take into account the heating up? Because it is very, very important to do that. So you see the transformation of the nickel sulfides is very quick, and you see there is not a lot of tailing. It is very steep, and even if it is coming from practice, it's still looking the same. So what is then really happening? This is another thing, I go through that because I don't have the time. The conclusion of that is that the nickel sulphide is not the real reason for, at least not the base of the curve. The base of the curve is the heating up of the glass. Because imagine what you are doing in a heat soak test. In a heat soak test, you put, let's say, 5 or 10 tons of glass into a furnace. Then you heat it up. But heating up does not mean that all of the glass, every place in the glass is heated up in the same way. You blow hot air onto one rim of the glass. So what will happen? The rim will be hot and the center of the glass will be cold. What is the consequence? The consequence is that there will be tensions, surface tensions all over the glass. The glass might bow or not, but there are strong surface tensions, and these surface tensions are moving the glass. And if there is a reason to make the glass break, the glass will break. But this is independent of the real reason. I showed you the example of lots of breakages because of silicon dioxide inclusions. You know the dilatation coefficient, the expansion coefficient of SiO2 is much lower than that of glass. Nickel sulphide has a higher expansion coefficient. Nickel sulphide has a transition. SiO2 does not. So there is absolutely big differences, and so there is one reason, that is the temporary stress. Another reason might be, and this is not on the slide, another reason might be that there is, due to the heat, a difference in the subcritical crack growth that is supposed to be stronger at higher temperature. Well, time is running out. Unfortunately, I have to skip this, and I'll show you just one example from our own experience at Saint-Gobain. At Saint-Gobain, we do the heat soak test since about 2002. And this is since the pre-norm of the 141679 was established. It is in operation since 2006, but there was the pre-norm, and we followed this pre-norm. So since that time, at Saint-Gobain in Germany only, we tested about 40,000 tons of of glass. We heat soak tested that. It was in 3 factories, and this is proven by statistics. We have found 6,500 breakages in those 40,000 tons. This makes about a breakage ratio of 6.2 tons per break, or 1 break in 6.2 tons. This is a quite normal value. It's a value that I also used in other publications to make some estimations. But the breakages on buildings from these were virtually zero. There was nothing. There was some 4 breakages were reported during that time from this production time, and all those were from 2009. They were coming from the same factory, and they were at 2 building sites and in similar built-in situations where there was no danger for life. So you may think what you want about that, because I think okay, let's take that serious and make an estimation on that basis. So then the quota would be 1 breakage on 10,000 tons of glass. That makes that the efficiency of the heat soak test is 99.94%. Or if you reverse it, you have 0.06% of residual breakage risk. So the estimation from before was that that would be 1.5%, because the efficiency of the heat soak test should be 98.5, so the residual would be 1.5. But you see that this is not breaking on the facade, and the heat soak test is by a factor of about 25-fold better than presumed. So if we reverse that, 1.5% would be about 100 breaks on these 40,000 tons of glass. So if we really would have that, it would be about 7 per year, just in Germany, and only from Saint-Gobain. I don't know our market share. It might be maybe 20% or something like that. Let's estimate by that. Then we would have 5 times 7 makes 35 breakages in every year on the buildings with the heat soak tested glass. And we know that this is not true, is not possible, because This would be in every newspaper, the glass rain in this and that building. We have seen that often enough, so we know this is not true, and we know that we have no problem with the heat soak test. Well, okay, I don't go into the summary, I don't have no time left. This is my very short summary. I tell you that, in my opinion, if the glass is heat soaked, then the glass is safe. And you can read my publications. You see here, this is free on the internet. You can download and you can read it. It is about 92 pages. So it is all my knowledge that I have is in those papers. And if you are able to digest, you will be able to judge. Okay, thank you for your attention.
Thank you, Andreas. Very interesting. Are there some questions? Yes, please.
Very shortly, Mr. Kasper, so because my voice is not working. The problem is that there is in the standard a very strange sentence that says that 1 every 400 tons of breakage could be allowed. And it's not clear which this 400 tons is related for.
Okay, but
this is a very big problem because when you have a breakage, the question arises about the 400 tons, if they are related to the same order, the same thickness, the same glass, all the production of the factory. That create a bigger confusion.
Well, so the 400 tons are coming from the generation, if you like, of this standard. Because this standard was generated, it was based on the first step on the building that you maybe know is the Deutsche Bank building in Frankfurt. It's a double tower and it contains 400 tons of toughened glass. So the owners of this building did not want to have one breakage. So what they did at the time was they made some tests with the heat soak and they fixed at that time 8 hours of holding time, and after 8 hours of holding time they didn't see any breakage anymore. So they said, okay, if it's like that, then we will probably have no breakage anymore, and this is the reason for the 400 tons. It's just a calculation value. And it is only a calculation value for the heat soak test. It's not a calculation value for the Deutsche Bank. Because in the Deutsche Bank, we did not have one breakage up to now, as far as I know. So 400 tons means 400 tons, and 300 tons is a weight. It is not depending on the size, on the thickness of the glass. It's just a number. So I don't see where the problem is. Can you try to explain again? Or maybe we can discuss later if you want.
We'll discuss later, because we have the same discussion in the European Committee and we don't have any progress about that. We can discuss later.
Okay.
Any other questions? No, and I propose to have a big hand for Andreas again. And
hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao!